What does your phone, camera, computer, or even your car have in common? They all rely on capacitors to store and release electrical energy in an instant. In this lesson, you'll learn exactly what capacitance is, how to calculate it, the current to voltage relationship that every engineering student should know, and also how to determine the power and stored energy of a capacitor. And we'll wrap this presentation up with simplifying the capacitors when they're connected together in series or parallel, and just give you a strong confidence on circuit analysis when exposed to capacitors. So let's get right into it. To kick it off, let's start with understanding what an ideal capacitor actually is. And an ideal capacitor is an energy storage circuit element representing the electric field effect. Capacitance can be measured in farads, which is given the symbol F, and capacitance can be a variable C and is known as just being a constant, which is determined by the geometric configurations of the two conductors of the component. And you would take the charge on each conductor, dividing that by the potential difference between the two perfect conductors of that element. The illustration here is the general circuit symbol for a capacitor, where the current entering one terminal of the capacitor is equal to the rate of buildup of charge on the plate attached to that terminal, which is equivalent to the capacitance multiplied by the rate of change of voltage across the capacitor. The voltage can be obtained by rearranging the formula for the current through a capacitor and then integrating both sides of the formula to obtain the voltage across the capacitor over a period of time. The instantaneous power delivered to the capacitor is given by taking the voltage across the capacitor multiplied by the current. Now recall earlier when we defined the formula for the current across the capacitor, that formula can be substituted into the instantaneous power equation, resulting in the power equaling the capacitance multiplied by the potential difference time of the rate of change of voltage. Assuming the capacitor voltage to be 0 at an initial time, the stored energy in a capacitor at time t is given by taking half the capacitance multiplied by the voltage squared. Alright, so let's say we have two capacitors, C1 and C2, and they're both connected together in series. And for the two capacitors in series, they are known for sharing the voltage, and that is in direct proportional to their capacitance values. And while the current flows through them is the same. Using Ohm's law, the voltage across the circuit can be calculated by taking the current divided by the equivalent capacitance of the series circuit. The equivalent capacitance is found by taking the sum of the reciprocals of the capacitors and then inversing the sum, which would represent the equivalent capacitance. Alright, that's enough about series connection for capacitors. Now let's focus on capacitors connected in parallel. Here we also have C1 and C2 representing capacitor 1 and capacitor 2, but now, like I mentioned, they're connected in parallel, so that means the voltage across capacitor 1 and capacitor 2 are now the same. So using Ohm's law, the current across the circuit can be calculated by taking either the capacitance multiplied by the rate of change of voltage, and that can be simplified by just taking the equivalent capacitance multiplied by the rate of change of voltage. Therefore, the equivalent capacitance is simply just the sum of capacitor 1 and 2. And that's the same boat if you were to introduce 3 or 4, whatever, how many capacitors in parallel. Okay, that concludes the video. So if you stuck around and found this useful, was a great introduction, crash course, or even a refresher, I really appreciate it if you like and subscribe. It would really support the channel out. Make sure to check out other videos if you are just continuing this educational journey, and I hope to see you guys in a later video.